Use the substitution x equals sec theta to show that the integral is equal to root 6 minus 2 over root 3. All right, let's go for it. So we've got this, and that means that dx by d theta is sec theta tan theta. I really like the function sec theta because, when you do the derivative, you get the same thing, and then you times by tan theta. That's using the quotient rule, it's just a standard result. It is worth knowing, to be fair. Okay, and then we've got that x is equal to 2. So, hold on. So that means that cos theta is 1 over x. So theta is inverse cos of 1 over x. And therefore theta here is going to be inverse cos of a half, which becomes pi over 3, sorry. And then if x is equal to 2, then theta is inverse cos of 1 over root 2, which is 45 degrees, or pi over 4. So our integral, which I'm going to define as this, is going to equal the integral from pi over 4 to pi over 3 with our new limits, 1 over sec squared theta minus 1 to the 3 over 2. And then I can replace dx by d theta. That's using the chain rule. Sometimes people like to just rearrange it to make dx the subject. You can alternatively do that. I prefer to do it like this because I don't know, it's just I don't like the idea of just timesing through by infinitesimals, basically. Like you've got to remember that this thing is like an infinitesimal amount, and it doesn't, we haven't really proven um that we can just start timesing through by it. So I always just go with the chain rule, which we can prove. It's not too bad. So this becomes sec theta tan theta d theta. Okay, right, what are some identities? We've got that sine squared plus cos squared is identical to 1. So if I divide through by cos squared, I get tan squared plus 1 is going to be sec squared, which means sec squared minus 1 is going to be tan squared. So sec squared theta minus 1 to the power of 3 over 2, I'll just do it over here, is going to be identical to tan squared theta power of 3 over 2, which is going to give me tan cubed theta. So this becomes 1 over tan cubed theta sec theta tan theta d theta. So that tan theta is going to cancel with one of these, leaving me a 2. And then I can write it as sec theta cot squared theta d theta. And I'm nearly there. So at this point, one thing you might try and do is use inspection and think, right, what if I raised the power of cot to cot's cubed theta? Do I then get, like, does that work when I differentiate it back? But actually it doesn't, because when you differentiate cot, you get minus cosec squared theta. So it's not going to quite work out. So what I decided to do was get it all in terms of sine and cos, just to see if that would work. And it turns out that it does. Because sec theta is, and I'm going to write down here, sec theta is actually 1 over cos theta, and cot theta is cos over sine. So I get cos squared theta over sine squared theta here. And the 1 over cos theta cancels one of these out. So I actually get sine theta to the minus 2 times cos theta d theta. And this is in the form of sine to the nx cos x, which has a very nice result because all you do is raise the power by 1 on sine, When you differentiate, that's your trial function. When you differentiate that back, you get n plus 1 times sine to the nx, and then you times by the derivative of the inside. The inside function is sine x, because it's actually sine x all to the n plus 1. So sine x is the inside part, so we just need to divide by n plus 1, and obviously a plus c here. So it's the same idea now. Well, this is the definite integral. So I'm going to raise the power by 1 to make it sine theta to the minus 1. Right, when I differentiate that back, I get minus sine theta all to the minus 2, because I lower the power, and I times by the derivative of sine cos theta. So all I need to do is put a minus in there to make it work. Pi over 3, pi over 4, ready to substitute in. So I get minus 1 over sine of pi over 3, and then minus minus, that becomes plus 1 over sine pi over 4. This becomes sine of pi over 3 is root 3 over 2, so it's actually minus 2 over root 3. Sine of pi over 4 is 1 over root 2, so I get root 2 here. Put it over a common denominator by times in top and bottom by root 3. I'm going to get root 6 over root 3 for root 2, minus the 2, root 6 minus 2 over root 3. And that's just about fitting it in, is the answer that we wanted for I, as shown here. Before I move on, I'm just going to go through this integral in one other way. I don't think it's quite as intuitive, but it is nice. So instead, I'm still integrating now back to sec theta cot squared theta. Okay, and actually, here's the thing. Cot theta is equal to cos theta over sine theta, which can be written as 1 over sine theta times cos theta, which is actually the same as 1 over sine theta divided by 1 over cos theta, which becomes cosec theta over sec theta. Do you know what? Before this question, I'd never actually written all that before. But what that means is that this integral is going to be sec theta times cosec squared theta over sec squared theta d theta. So the sec thetas cancel, and then I'm left with cosec theta over sec theta times by cosec theta. I'm integrating with respect to theta. Now I just showed a minute ago that this was cot, so I can actually write this whole integral as cot theta cosec. It's amazing how differently you can write integrals, but they're all the three that I've done, that one involving sine and cos, they're all exactly the same. And actually, this has got a really nice result, because when you differentiate cosec, you get minus cosec cot theta. So this simply becomes minus cosec theta, in this case plus c. Of course, in the question, we then substitute the limits in, and you'll get exactly the same answer. So I just wanted to share this. It's not how I did it, and I wouldn't have thought to do it like this, but now that I've seen it, then maybe I will in the future. All right, that was just part A. Part B then asks us to use integration by parts to show that this integral on the left is equal to this on the right. Okay, so I'm going to say that this integral is j. It's worth just spending a little bit of time thinking about what you're going to let equal u and what you're going to let equal v dash. Thing is, if you let this equal v dash, you've got to integrate cosec like straight away, and then you're going to get an awkward derivative for cot. Meanwhile, if we're differentiating this, well, we have to integrate this, which is not, I don't actually think we can. In fact, the way to go about it is to take a bit more time to think about it and rewrite it as cosec theta cot theta times cot theta. That's a bit better. Because now, right, remember, I've already talked about this one before. We're going to let this one equal v dash, which means that v is going to be minus cosec theta, and this one can be u. So then u dash is the derivative of cot theta is minus cosec squared theta. So I get u v minus u dash v, which gives me cot theta times v, so cosec theta, just with a minus there. And we can see that there. And then I'm minusing the integral of minus cosec squared theta times v, which is minus cosec as well. So I can just change it to a 3 here and get rid of the negative. All right, brilliant. All right, now let's just focus on this integral, which is a bit of an awkward one. But there's a similar trick you can do with sine cubed. With sine cubed, you can write it as sine times sine squared and then rewrite sine squared as 1 minus cos squared. So I'm going to do a very similar thing here. Cosec theta times cosec squared theta, but remember our trig identity, sine squared plus cos squared is 1. Divide through by sine, 1 plus cot squared is cosec squared. So replace this by 1 plus cot squared theta. And this is going to give the integral of cosec theta d theta plus the integral of cosec theta cot squared theta. Now let's just take a look back at the original j. Actually, it's the same thing. This is j. So what I have overall is that the integral, so therefore, actually I'll keep it in terms of j. J equals minus cot theta cosec theta minus the integral of cosec theta d theta minus j. I'm using the minus because that's where it is there. I missed that out before. And what I can do now, it's a really nice trick in integration, is just add the j onto both sides to make it 2j. So 2j is going to be minus cot theta cosec theta minus, and now I'm going to rewrite this integral as, so it's cosec theta d theta. And this one is actually in the formula book. It's ln cosec theta plus cot theta with a modulus around it. And then we're going to get a plus c in the mix as well. Let me just check the final answer. Does it include plus? Oh, it does, but outside the bracket. So I'm going to call it, I'm just going to call it k for now because I'm going to be dividing by 2 in a minute. Now this is actually an awkward integral. I'm going to talk a little bit about it because one way to do it, there is more than one way, but we're going to rewrite it as cosec theta and then actually times through by cosec theta plus cot theta, which is not an obvious thing to do at all. And actually, by the time you've done this, you might as well have just learned what the answer is. But this is how you can do it. So that then gives cosec squared theta plus cot theta cosec theta all over cosec theta plus cot theta. And this is actually in the form of f dash theta over f of theta. If you differentiate cosec, then you get cosec cot. So that one differentiates to that. And if you differentiate cot, then you get, sorry, you get minus, I think I've made a mistake here. I think that should become a plus. So this is a minus here. Yeah, sorry. So I need to put a minus here and a minus here, and then take the minus out of the integral. Okay, now it's in the right form, because when I differentiate cosec, that's it. I get minus cot theta cosec theta. And if I differentiate cot, then I get minus cosec squared theta, because tan goes to sec, cot goes to minus cosec. The ones that start with a C always differentiate to negatives. So I'm going to get a negative. So that's basically a little proof, because then I'm going to get I'm going to get minus ln of the bottom cosec theta plus cot theta plus C. So in our case, we're going to have that J is going to equal, let's just check with the answers that I haven't made any mistakes. So it's going to be, yeah, now I've made it positive because I've got a negative of a negative. So J is going to be a half of ln cosec theta plus cot theta. And then I'll be minusing cot theta cosec theta. Good, as it is there. And then I'm going to be adding k over 2, which I'm just going to call c, like they do in the answer. So c is equal to k over 2. And that is our answer as required. Cool. This takes us to the final part of the problem, and you'll understand why this is question 7. Okay, we've now got the original function that we had, this thing here, and previously we worked out the area underneath, but now we're being asked to find a volume of revolution, and the whole thing is rotated around the x-axis. So in general, we get that v is equal to pi integral of a to b of y squared with respect to x, because essentially we're adding up lots of infinitesimal cylinders, and then times, well, the pi is involved there as well, but you can take the pi out, and that will give you your volume of revolution. So for us, we want to find v equals pi integral from root 2 to 2 of 1 over x squared minus 1 to the power 3, because I've squared the function already with respect to x. Now I don't have to start from the beginning, because this is very similar to the integral that we did in part A. So I can let x equal sec x. And what is going to happen is we're going to get pi integral from pi over 4 to pi over 3. And then just moving back up here, we had let me just highlight the bit we got to. So this bit here, actually, let me take it from here. This bit here, I just need to get rid of the divided by 2. So it's going to be 1 over sec squared minus 1 to the power 3. and then I'm times in by, I think it was sec theta tan theta. So this is using part A. Okay, and then that is going to become pi integral pi over 3, pi over 4. Remember, this bit here was actually tan squared, so it's going to be 1 over tan to the power of 6. So I'm going to get sec theta over tan to the power of 5 theta d theta, which I can then write as pi, pi over 3, pi over 4, sec theta cot to the power of 5 theta. Now, I'm going to call this integral here, I've got one that was I, one that was j, I'm going to call this k. We'll bring the pi back in at the end, because there's lots to do here. So remember in part B, we had the integral of, actually, let me just remind you, cosec theta cot squared theta. So this one, let's try and get it in the same kind of form. We've got cot to the 5 theta. That looks pretty awkward. So what I'm going to do is I'm going to write cot to the 4 theta, and then cot theta I can write as cos theta over sine theta. Or I could write cosec over sec. I don't know, I just found it a little bit easier to do it this way. Then the sec and the cos cancel, and the 1 over sine can be written as cosec, and we've got it again in the right sort of form. The reason we want to go with this, just like in part B, was that cot and cosec have like a relationship. When we differentiate cot, we get minus cot cosec. So that's why it's good to go down that path rather than involving sec. So cosec theta, and then I'm going to actually go straight in and use the idea from part B, write it as cosec theta cot theta, and then cot to the power 3 theta. So in the earlier question, we didn't have cot to the power, where has it gone? We just had cot theta, but we can do a similar sort of thing. So see, this is where I'm going. I'm going to integrate by parts again. So this is going to be v dash, and this is going to be u. So v is going to be the integral of cosec theta cot theta. Well, cosec differentiates to minus cosec cot, so I'll just put minus here. And then u dash, I can use a chain rule. So 3 cot squared theta, and I times by the derivative of cot, which is minus cosec squared. So I'll put minus here. Brilliant. Right, now I've got my, let's just write it out again, integration by parts. So uv evaluated between pi over 4 and pi over 3 minus the integral of u dash v evaluated between the same limits. So in our case, we've got cot to the power of 3 multiplied by minus cosec theta minus the integral, oh sorry, yeah, that's okay. Right, then I've got minus 3 cot squared theta cosec squared theta, but I also need to times through by v, which is minus cosec, so actually this is going to be to the power 3, and the double negative means that that negative is going to go. Okay, now I'm going to focus on this integral. All right, let's have a think about what to do. So remember previously in part B, where's it gone? I got to a very similar point and I changed cosec squared into 1 plus cot squared. So let's do the same thing. This here is going to be, well, I've got cosec cubed this time. But let me just focus then. Let's forget about the -3 bit. Just we've got cot squared theta, cosec theta, and then cosec squared theta. Going to change that, just like before, to 1 plus cot squared theta, which means the integral is going to become cot to the power of 4 theta cosec theta d theta plus the integral of cot squared theta cosec theta d theta. Okay, this is actually in some ways looking more complicated, but in other ways, if you spot it, this is actually fantastic because we've got the integral of cot to the 4 cosec, and that is exactly what I defined k to be up here. This is just k. So bringing it all together, I've got that k is equal to minus cot cubed theta. I'm just taking this part here again. Cosec theta evaluated between these limits. And then I'm minusing 3 lots of this integral that I just worked out. And that is going to be k plus the integral from pi over 4. Do you know what? Let's expand the bracket as well. So it's going to be minus 3k minus 3 lots of this integral. Oh, which means, actually there's a couple things that this means, because actually this cot squared cosec theta is in fact what I worked out over here. So I've already got this result. Since I need to evaluate it between pi over 3 and pi over 4. So this is using part B. So before I launch into this and try and figure out what it is, I've got this one to deal with, like cot to the power of 3 theta evaluated at theta equals pi over 3. So let's just write down tan of pi over 3. That's the same as tan 60. It's actually going to be root 3. Cosec pi over 3 is then, I think I had this earlier on, it's 1 over sine of pi over 3. So it's 2 over root 3. And then tan pi over 4 is just 1. And I definitely had this one earlier. Cosec pi over 4 is root 2. So that means that 4k, because I can add 3k to both sides, is going to equal minus, and now I'm going to substitute in my values. So cot cubed theta is going to be 1 over root 3 cubed, because I have tan of pi over 3 is root 3. So cot of pi over 3 is 1 over root 3. Then I cube it. And I times by 2 over root 3. And then I'm going to minus, so it will become a plus. Cot of pi over 2, that's just going to be, sorry, not pi over 2, pi over 4. So that's going to be 1 as well. So I'm just going to do 1 times, and then I've got root 2. 10. So that's the first bit. And it's going to be minus 3 over 2 times by ln cosec pi over 3 plus cot pi over 3. Sorry, that should have a modulus around it. Minus cosec pi over 3 cot pi over 3. Minus ln cosec pi over 4 plus cot pi over 4. Then minus minus, so plus cosec pi over 4 cot pi over 4. Okay, I've got 1 over root 3, which is going to become 1 over 3 root 3. Then I times by it again. This actually is going to become minus 2 over 9. This term here. Then I'm going to add on root 2. Minus 3 over 2 ln modulus. We've already talked about cosec, so we're going to have 2 over root 3 plus 1 over root 3 minus 2 over root 3 times 1 over root 3. Minus ln. Sorry, my mouse, my pen again is just, I think I've just made this video really long, and my my computer can't deal with it. So cosec pi over 4 root 2 plus 1 plus root 2 times 1, which becomes minus 2 over 9. Sorry, fast forward if you need to. Plus root 2 minus 3 over 2 ln 2 over root 3 plus 1 over root 3 is 3 over root 3, so it's ln root 3. Then minus 2 over 3 minus ln. And I just realized the whole thing should be times by 3 over 2. My bad. Okay, so this is equal to minus 2 over 9 plus root 2 minus 3 over 2. I can bring the luns together. So it'll actually be ln of root 3 over root 2 plus 1. And this is necessarily positive, so I can just ignore the modulus. Then I'll be adding 1. So I'm dealing with that, and then I'll be minusing 3 root 2 over 2. Remember, that is equal to 4k, which means that k is going to be a quarter of all of this. Now, it's definitely just worth having an eye on the answer, which is here. So don't forget, k, we actually have to still multiply it by pi to get back to v, because k was the actual integral. I didn't worry about pi because I just thought that would overcomplicate it. But maybe I'll bring it back in now. So finally, v is going to be pi do you know what? Let's leave the 4 out for the moment, I think. So pi over 4. Okay, then I've got minus 2 over 9 plus 1. That's 9 over 9. So I'm going to be left with 7 over 9 from those two. That's good. I've got the lun's the other way around here, but that's because of this minus. So if I make it a plus here and raise it all to power of minus 1, sorry, I probably should have done that to start with. Then I'm going to get plus 3 over 2. Let's try that again. Then root 2 plus 1 over root 3. You can see it, we're nearly there. All right, this is a bit of an issue, but I can change this to 2 root 2 over 2, and then I can add this and this together, leaving me minus root 2 over 2. And I think I'm pretty much there. So finally, I can multiply through by that quarter and just rearrange a few things. So my second term is going to become 3 over 8 ln of all of this. Come on, so close. Then I times 7 over 9 by a quarter, which gives me 7 over 36, hooray. And I times root 2 over 2 by a quarter, which gives me minus root 2 over 8. Of course, it's absolutely fine to use this final answer just to guide you towards the end and potentially locate any mistakes that you might have made. Okay, and let's just finally bask in this glory of having found this answer. Oh, okay, well done. just going to give a very quick overview of what has just happened here. Back up to here. So at the start, we did a substitution for sec theta. That just seems a long time ago now. We got it in terms of, we got it as sec theta, cot squared theta. Even that was quite involved. I talked about two different ways to do it. I quite like using sine and cos, but I also talked about an alternative down here, which I didn't quite finish evaluating, but it would obviously give the same answer. In part B, here we go. We had to, it was quite a lot more involved. We had to integrate by parts, and the trick was to actually write it as cosec times cosec cot and integrate by parts using these. That just made life so much easier. Are there alternatives? I'd be interested to know if you could do it other ways. I'm not going to look into it here. I've already been talking for, I don't know, half an hour or so. So worked through it and everything. Really nice. Like I've seen other integrals in AEA where you get kind of the integral itself in there, but this is like just an even harder version of it. This is question 7, but then it all worked out as needed. And we even talked about the integral of cosec theta. That led us to the finale, this 8 marker, on finding the volume of revolution of this function here, which we get this. Looks like, just even from the start, this looks like, whoa. And we figured it out. We used the other parts, of course, to help us. It was guiding us along to this final result. And we used part A to help set up the integral, getting cot to the power of 5, using the ideas of part B to write it as cot to the power 3 times cosec cot, integrating by parts. There was still more to do then. Bringing back in the 1 plus cot squared theta. I didn't talk about that, but that was a big thing in part B to help do the integral. And we managed to then get the integral k again inside the solution, but this time we were timesing it by 3. We had to then evaluate this, which took a bit of, you have to do it carefully, evaluating this term here and evaluating this integral, which fortunately was the integral from part B. So you can be pretty confident when you get to there that you're doing it right. The fact that B comes back in, and we could just use that result. So even if you couldn't quite get that result in part B, you could still in theory do this question. Follow through all of it, very carefully manipulated it, brought it all together to get the answer required, and there we are. So once again, I just want to say well done, thanks for watching, and apologies there's been some lag, and some of my solutions have had to go quite slowly, but I hope it's made sense, and keep going. Really good question.